Okay, so here we go. I'm going to attempt my second tutorial video on the regression analysis data challenge that we never got to in class, but it should help you do your homework assignment that's due next week on regression analysis. So I'm looking at the literacy data set that's available in Blackboard, and the first thing that you want to do when you're looking at this type of data is to read the code book if there is one. So this is old data, it's not mine. Somebody put it together. But we have these variables. I'm not so concerned with these this time around, but I have a population, variable population in millions, whether it's democracy or not democracy, percentage of the population that is literate, life expectancy in years, average years of schooling, and GDP per capita in thousands of dollars. The first step in a regression analysis really would be to go through these variables and determine what literature supports the relationship between some of these predicting one of the other ones. In this case, democratic state is a dichotomous variable. It's a 0 or a 1. And because right now we're just learning sort of straightforward, traditional linear regression, that might seem like a good choice for you, but we don't have the skill set to interpret that just yet. That would be your next statistics class. So don't choose that. We wouldn't choose that as our dependent variable, though it might be a good one. But in a perfect world, you have a data set where you are looking at these variables and you're trying to decide what the theory says one dependent variable is predicted by several others, or one other or more of the independent variables. So I'm just going to pick randomly just to do an example. I have this data set here, and again, I'm not going to mess with any of these code names or regions or any of these categorical variables. The first thing that I want to do is to use the data analysis button, magical button, and find in here regression, because I'm doing regression analysis. And the first thing that it asks you to do, I'm sorry, mine's already filled in, but these should be blank in yours. If you hit the up arrow right here, you'll see this little box pops up, and what you want to do is, it says input Y range. Input Y range is the same thing as your dependent variable. So this is the variable that you want your model to predict. Now, I'm just going to pick a random dependent variable. So the literature does not support this. I don't endorse this analysis, but I'm going to pick here the KGDP. So I'm going to see if literacy and life expectancy and maybe schooling predict GDP. Again, there's no theory behind this. So I want to select this whole column here, and if you remember, I clicked the first cell, I scrolled all the way to the bottom, and I shift-clicked this one, which I think is Apple click if you're on a Mac. And then I want to pick my, what they say is an input X range. These are your independent variables. So I'm just going to pick these three right here for no particular reason. And because I'm just going to pick three, I'm going to actually click and hold and then just drag this to select the whole field. There are better shortcuts to do this, but the data set's not that big. So here I have my dependent variable selected, that's in the J column, and my independent variables, which are G through I columns. And here you want to make sure, because the first line of our data, this bolded line, is labels, and I want to make sure that Excel doesn't think it needs to calculate those, because we talked about this in class, but Excel is not really good at missing values or messy data where you have something that's non-numeric. So you want to make sure you tell it that you have labels, and I just want to put it in another worksheet in the same workbook. And then you'll see here I already have these checked. If you've never done a regression in your Excel data analysis package before, these won't be checked, but just make sure that you check these, and I'll show you why in a minute. And then after you've had your data entered, you just hit OK. Wait a second, and it pops out this mess. Now, I don't know why this has something to do with these old data sets that I'm using, but it puts everything out in this terrible font. So before I touch anything, and while it's all still highlighted, I'm going to go to Home, and you can see it's doing all this in Courier 8, which is hideous. So I am going to pick Arial, I don't know, something bigger so you can read it. And when I double click these columns, you'll see it automatically adjusts to be the widest range to fit all of those numbers in. That way I can read the whole, I don't like that one, that's too big. I can read the whole column. I'm not really worried about these so much. Okay, so I'm going to walk you through what just happened. We just did a regression analysis, and this is all of the automatic output that Excel spits out for you. And down here, this stuff is not something that you really have to worry about. This is just Excel printing all of the output that it used to do some of these plots over here. So I'm going to start up here in this regression statistics box. Now, we talked in the regression analysis lecture about these values right here. And here's my R-square value, and R-square is basically a measure of the fit of my model. How well did my independent variables predict my dependent variable? And you'll remember that I'm just stabbing in the dark here, so there's no theory, though there should be, to back this up. Which means that if you had used theory and some sort of sense of logic to do this, in social science models you don't expect this number to necessarily be very big. But if the theory backs it up, then you still have a model that's worth exploring. In our case, we have an R-squared of 0.734, so about 73% of the variation in our dependent variable is explained by our independent variables. And we talked about this in class, but as you add more independent variables to your model, you will necessarily drive up your R-squared. So when we have multiple independent variables, we have 3, you often want to look at this adjusted R-squared. So it compensates or tries to compensate for the fact that there are more than one independent variables in the model. And you can see it's not that much different in this case from R-squared. And here you'll note that we have 110 observations. So that's how many data points were in the data set if you didn't notice before. Now, Excel provides this Anova table right here. And we talked about Anova a long time ago, and I mentioned this in the regression analysis lecture. But this Anova model is testing the null hypothesis that there is no difference between your independent variables coefficients and 0, so that it can't tell the difference between any of these. And the Anova test the alternative that there's at least one that's different. And so most often, if you have any kind of model that has some predictive power, this is going to be true. It'll at least be able to tell that one of the independent variables is different. But, and I want you to remember here that this e to the negative 30 means that this decimal place goes 30 places to the left, which makes it a super, super, super tiny small number. And our mantra is, when p is small, we reject the null. So this Anova table is simply telling me with this that at least one of the coefficients is different. Okay, before we get to that coefficients though, one of the assumptions of regression is when you have multiple independent variables in the model is that those independent variables don't have a really strong relationship with each other. We talked about this in terms of correlation. And I just want to check that in my data before I go and interpret all of this stuff and spend that time. I want to make sure that I understand whether or not my assumptions are met. So I'm going back to the original data set, and you'll recall that G, H, and I, these 3 columns right here, are my independent variables. So I'm going to go back to the data and the data analysis tab and find the correlation option here. Click OK. And it asks me what my input range is. So I'm going to select these 3 columns again, my independent variables, and click the down arrow again. Make sure you indicate that it's grouped by column since our data is organized this way, and that you have labels in the first row. And I just wanted to put this matrix, this correlation matrix, out in a new worksheet. And I hit OK. So here's my correlation worksheet. I'm just going to rename this so I don't get them confused. And what you see here is a terrible font set. I'm going to go back to this Arial, whatever, let's do 16 so we can see it really good. You'll remember here that along this axis here, the correlation between literacy and literacy is obviously 1. It's a perfect correlation because it is itself. Now, correlation, the closer that this value between these 2 variables gets closer to 1, whether that's positive 1 or negative 1, the closer it gets to 1, the closer it is to a perfect linear relationship. And the closer it gets to 0, of course, there's no relationship, 0 for no relationship. And what you'll notice here is that these numbers are very, very correlated with one another. And I can tell you right now that this is going to be a problem. But we'll talk about what that looks like if you miss this step. And so this is a very high number. What is high, like too high? We talked about in class, it kind of depends. Again, sort of in reference to the theory. 0.6 is a benchmark, 0.7, but I mean here we're in the 0.8, 0.9, so we're very close to 1. This is a very strong linear relationship. And 2 of these should strike you as not that surprising, right? That the number of years, the average number of years that a person spends in school and their literacy rate should be correlated, assuming that school teaches them anything. And here, and I'm sure there's literature to back this up as well, but then the number of years you're in school on average probably affects your life expectancy because of education about health and well-being, and also prospects for types of employment that you can seek. And literacy and life expectancy are correlated, the average life expectancy, probably for the similar reasons as schooling and literacy. But in a real regression model, if you're doing this for real research and not some practice homework assignment, you would need to look into the theory and see why this is and whether or not you should continue with this model or look for different variables. And in this case, what this would say to me, if you found theory that said that these all should be in the model, that maybe what you should be thinking of is trying to combine these 3 variables into one index, or maybe schooling and literacy should be in one index so that you're not getting this multicollinearity. Okay, so I have this regression model, and you'll notice, and we didn't really get to this in class, but it is important, that Excel prints out these graphs for you, which I'm just going to show you really quick. This normal probability plot is sort of one of the baseline graphs that you should look at. And you'll remember that one of the assumptions of linear regression is that the underlying data is normal. And this graph is a visual representation of whether or not your data meets that underlying assumption. So, I mean, I'm sure you can look at this and see that it's not a great looking line. Linear regression should make lines usually. And what we would look for in a perfect version of this world here is a 45-degree angle straight line going this way. And you can see that we don't actually have that. This indicates that there's some sort of possibly something going on with outliers that are changing the shape of this and making the data appear to be not normally distributed. So this shape, and you don't need to quantify it or come up with anything, you can sort of wave your hands at it, and art more than science at this point, but basically what you want is a straight line, and this is not a straight line, And so that's bad. We're just going to go with that is not a good thing. I'm going to set this over here for a second. The other one I want you to notice are these residual plots. I'm going to start with literacy. I haven't looked at these, so I'm doing this kind of on the fly, which I promised I wouldn't do. Okay, so in a residual plot, the thing that you're looking for is no pattern. In a perfect world, you would have things equally spread out on both sides of this x-axis here, so you'd have stuff on the positive, stuff on the negative, and kind of spread out this way, no clustering. And so it should look like somebody just like threw confetti at a table and it all just kind of landed somewhere. And this one actually doesn't look too bad. There's something happening at this end, and that sort of jives with what we saw in our probability plot. But the other thing that you want to think about in these residual plots is that residuals, we talked about this and I'm sure it got lost in the moment, but residuals are calculated in such a way as to emphasize outliers. And so you might notice this little guy right here. It even tells you if you hover over it, you can see which point number it is. You could go look it up in your data set and see what is at this point here in my residuals. And this little guy is probably causing some problems in our data, but we're not sure. And you should be careful to just immediately go and try to remove remove outliers from your data set. Again, you need to think about the theory, what the theory says, what the context says, and whether or not that should be in or has a legitimate reason for being excluded from your data set. The example I gave in class was about the number of incarcerated per population in the world, and Lesotho and the United States being super outliers and whether or not those should be included or not. Okay, so here's the residual plot for life expectancy. And you see again here, there's another one. It's a bit of an outlier. I don't know, this doesn't look too terrible, but it doesn't look great, right? If you're thinking confetti thrown on a table, this looks like it follows a bit of a pattern, this weird hook-shaped pattern, which indicates there's some sort of systematic error happening in our model. Okay, I'm going to set this one aside for a second and look at our last residual plot. Now this one actually doesn't look too bad. Again, something sort of systematic happening towards the tails. There's an outlier here. And so these aren't really terrible. One of our major concerns at this point is that we know that our correlations are very, very high. So we have a multicollinearity problem. Okay, so here is our regression output that we're going to look at right here. I'm not going to do the confidence intervals. I'm going to stay with this part of the table. And what we're looking at here is a hypothesis test. So do you remember I mentioned in several lectures that there's basically a generic flavor of hypothesis test that you can revert back to that helps you interpret lots of statistical tests, and regression is one of those, where the null hypothesis is that this variable is not different from 0. So this variable is equal to 0. That's your null. And I'll write it down for you. H naught is variable equals 0. Really not the variable, but the coefficient of the variable. The influence of that variable on the dependent variable isn't different than 0. It has no influence, however you want to think of that. And this one is that the variable is not equal to 0. Okay, so when we assess each of these p-values here, I have a really small p-value, and I can say I'm going to reject the null hypothesis, and therefore this literacy variable, even though it looks like it's very close to 0, right? It's a negative 0.1, is actually statistically different from 0. And I can go through each of these, and in this case I have all three of them, which is inconvenient for my example. Whoops, don't do that. All three of these are statistically significant. Right, they're all very small. You'll remember here that this e to negative 14 means that this decimal point moves 14 places to the left, which makes it the smallest of all of them. And that means that all of these matter in predicting the dependent variable. Now, you'll recall, of course, that we have some issues with our data because we have such super, super high collinearity between these. But just as an example of that output analysis, we're going to assume that none of those problems exist for a second. And what this tells me is that for an increase in literacy, so if literacy increases by 1 unit, I don't know how literacy is measured, then the GDP, KGDP, which is what we use as our predictor variable, this one, KGDP, decreases by 0.1 units. And I think GDP was done in per capita in thousands of dollars. So GDP would decrease by 0.1 times 1,000, and that's KGDP per, or dollars per capita. So you could do that for each of these. As life expectancy on average increases by 1 unit, which I would assume is 1 year, then GDP increases by 0.19 times whatever the units of GDP are. And then schooling, for every, I would assume, 1 year increase, I think that's units of years. Schooling, average years of schooling. So for every increase in 1 average year of schooling across the population, you'll see a rise in GDP per capita of 1.5 units. So that's 1.5 times thousands of dollars. So that's basically the interpretation of each of these. And in this case, we were so lucky as to have a conversation about a p-value not being statistically significant. But if it weren't statistically significant, then you basically, no matter what this number is, it could be 37, it probably won't be, but it could be, what that is saying, if this is a p-value that's large and we cannot reject the null hypothesis, that this model cannot tell the difference between this coefficient and 0. So it doesn't matter what you see it as, it can't tell the difference. And there are lots of ways to proceed from here that you would study in the advanced statistics class, but for our purposes, what I want you to understand is, 1, to understand how good your model fits, how much of the variance in your dependent variable is explained by your independent variable selections, and how to interpret these p-values and coefficients, so that you can say confidently that 1 increase in, and this is for you to interpret, I don't want you to say 1 unit of literacy. I would like you to go into the code book and say 1, I don't know what that's a bad one. 1 year increase in average life expectancy results in a, whatever this is times unit of analysis for KGDP increase in KGDP. So these two, literacy and KGDP, have a negative relationship, which I think is kind of weird. What this is saying is that an increase in literacy leads to a decrease in GDP, and this is where we're in a bit of a problem, because we have issues with our underlying assumptions. So we do have super, super highly correlated variables, and this is going to cause some multicollinearity problems, and you'll talk more about this in your advanced statistics class if you take advanced statistics. But generally, you don't want to have variables in your model that are so similar, right? Literacy and schooling are super similar, and so you might look to the literature and either combine them into an index find an index that captures both of them and use that data instead, or choose one over the other and assume that they are a proxy to one another. And it's not that bad, but I mean, this correlation is really, really bad. The impact on your analysis for this class shouldn't change. We're not getting into the depths of how you correct for this, but I would say that if you're working on your own projects, and even if you're working on the homework assignment, it's worth considering whether or not that variable or one of those variables should even be in the model. And what you would redo then is to do the regression over again, but drop one of those. So let's say I decide that actually literacy is causing the problem here, then I could go back to this, the original data, and I could do the same regression analysis, but instead of using literacy, I would just use life and schooling. So that would give me some sense of whether or not my model improves. Doesn't improve. If it doesn't improve, then you really should go back to the literature. I know I say that over and over again, but here we want to see if the model can improve from that, and whether or not we can correct some of the problems that are in the model. And at this point, actually, it doesn't look like it gets better. It looks like it gets a little bit worse. You can see that R-squared drops a little bit, but yeah, this still looks terrible. The other thing that we're going to have to fix in order to make this model work properly would be to find the outliers and decide if they should be removed or not removed. So there are a few problems with this model, but that is one of those things, and I don't expect you to be able to fix this in your homework assignment model. What I would like you to be able to do is go back to the slides at the end of the regression lecture and look to at least be able to talk about what some of the possible problems are with your data analysis. So if you see problems in the residual plots, I'd like you to be able to say that you see that there are some issues possibly with outliers, or in this case we saw some problems that looked, a little bit different in that it looks like in this life expectancy law there's something a little bit, a pattern happening. So there's not only an outlier, some sort of systematic error problem happening here. Just to remind you, these residual plots are plots of error, and so we can see in them, like this one, there's a bit of a systematic thing happening on this end too. And I'd just like you to be able to vaguely talk about that. Right? The residual plots indicate that there may be some issues with the data, including some outliers and some systematic bias, that the data, this is not going to be your results because I'm not using the same data set as you on purpose, but you would indicate that there were some highly correlated variables. You could run the model again without some of those, depending on whether you can justify that or not, which I did in this case. It didn't actually fix anything. It made it worse, actually. But that is essentially what I'd like to see out of your regression analysis. And you can include these or don't include these. You may want to include a residual plot that you find to be the most indicative of a problem. And you can include the normal probability plot and say that this is obviously a problem. There's something happening over here. Perfect one, or close to perfect one, and remember this is all about close enough, would resemble a straight line. And something wrong that the tails here indicate, and sometimes it happens over here, or a big dip in the middle, indicate that there's something wrong. And that something wrong is really for a later statistics class. For right now, I just want you to be able to recognize that the assumptions of regression have been violated in this case, and that means that there may be some problems with your model and it needs some further work. So that is my quick introduction overview, I guess, of regression using the data challenge assignment, and the principles should be largely the same for your homework assignment.